Okay, so in the last class we saw how to handle the solution resistance effect, right, whether we use a small amplitude perturbation or a large amplitude perturbation. We can modify the code that we normally use to simulate nonlinear EAS and account for solution resistance, and then we can find the actual spectrum incorporating the solution resistance effects. Now, I want to show you what happens when you apply KKT on data that comes from large amplitude perturbation. Okay. When we apply KKT, will it always detect nonlinearity, or will it detect sometimes and will it flag it as OK? And other thing is, we also seen that the code can be modified to account for instabilities and generate the spectrum when we have instability, whether KKT does a good job in detecting the instabilities. Okay. So, just to refresh your memory, if the system is linear, causal and stable, then the resulting spectrum will be KKT compliant, but it is a sufficient condition, it is not a necessary condition for KKT compliance. What it means is, it is possible that you may have a nonlinear system and that might be KKT compliant. If the system is linear, stable, causal, it is guaranteed to be KKT compliant, but just because some response says that it is KKT compliant does not mean it has come from a system which is linear, causal and stable. Okay. Now, we know how to generate EAS spectrum for cases with large amplitude perturbation. We know how to generate the EAS spectrum with instability, and you can of course always add some noise and see how the spectrum will look if the spectrum arises not just because of our perturbation, but also because of external noises. Okay. Now, we want to do the following. We want to generate a variety of spectra for different mechanisms and then see whether in all cases KKT can detect nonlinearities, in all cases can KKT detect instabilities. Okay. So, this is the methodology we used: evaluate few mechanisms, generate spectrum in the nonlinear regime using numerical simulation, and we aim to generate spectrum with different patterns. Okay. Then we apply KKT. There are many methods of evaluating for KKT compliance. Direct integration is one method. Okay. Measurement model approach is another method, and one variant of that is linear KKT software, which makes it easy to implement this measurement model approach, and then record whether this KKT program by integration or KKT validation by measurement model approach, whether both of them are able to flag the nonlinearities, under what circumstances are they able to flag the nonlinearity. Okay. To refresh your memory, under one condition we know for sure that the data will be KKT compliant even though it is coming from a nonlinear system. Okay. If you take a simple electron transfer reaction, and if you generate a spectrum, assuming there is no mass transfer limitation, assuming there is no solution resistance, in the complex plane plot we know the spectrum will look like this, going from high frequency to low frequency. Of course, this is the mid frequency, and if we apply a small amplitude perturbation, you might get a data like this for a particular scale. If I apply large amplitude perturbation, we know that it is going to still be a semicircle with a smaller value of charge transfer resistance and of course polarization resistance, which means the system can be modeled by a circuit like this. So, double layer capacitance here, and this resistance, when the perturbation amplitude EAS is 0 is small, this resistance will be a constant depending on the kinetic parameter values and depending on the DC potential, but that is going to be fixed. When we increase perturbation amplitude to make it 50 millivolts, 100 millivolts, this will become a smaller resistance, but still it is a constant resistance, constant impedance independent of frequency, and all these spectra will be KKT compliant. So, this is one clean example where we know that the system response is not linear and yet KKT cannot detect or KKT cannot flag and say that there is something wrong with this spectrum. So, it is possible that you have a nonlinear response and KKT will not be able to flag it. But will it happen in all cases? Will KKT say that all the spectra with nonlinear effects are KKT compliant? So, this work was published by a group in 2015. I will just summarize some of these results. We looked at 3 different mechanisms. The first mechanism is metal going to metal 2 plus into solution via one adsorbed intermediate. So, the first step is an electrochemical step and the second step is also an electrochemical step. We had tried this for a variety of kinetic parameter values. The next example is with a different mechanism. It is still metal going to metal 2 plus into solution, but via 2 adsorbed intermediates. The first and second steps are electrochemical steps. The third step is a chemical step. Third example is little more complex. The first and second steps are reversible electrochemical steps. Metal goes into metal plus adsorbed, releasing an electron. Metal plus becomes metal 2 plus adsorbed species, again releasing an electron. Third, the metal 2 plus goes into metal solution. So, until this it is similar to the second mechanism we had tried, of course, with reversible in the first and second steps are reversible. In addition, there is a fourth step. This is what we have referred to as catalytic step. So, metal, bare metal right next to a metal 2 plus adsorbed species, bare metal becomes metal 2 plus adsorbed, metal 2 plus adsorbed becomes metal 2 plus solution, but in effect metal 2 plus adsorbed which is consumed here is produced here. We have seen how to generate the mass balance and charge balance equations for this before. So, I will not go through this code or details. I will just mention that certain kinetic parameter values we use them and this is the spectrum that we get for small amplitude, for large amplitude, and then we take those data and subject that to KKT validation and see what the results are. Okay. So, first example is with one adsorbed intermediate with certain kinetic parameter values 10 power minus 9 moles per centimeter square per second for K1. The exponent for this is 4 volt inverse. K2 0 is of course 10 power minus 11, B2 is 20 and gamma is 10 power minus 8 moles per centimeter square. And if you apply a DC bias of 0.4 volt versus OCP, right, this is in the anodic regime, and in that case if you use 1 millivolt, it is definitely in the linear regime. If you apply 1 millivolt perturbation, 2 millivolt perturbation and compare the spectra, they will overlap, and if you apply very large perturbation 300 millivolt, the spectra that you get are like this. 1 millivolt shows clean, well separated 2 semicircles. This 300 millivolt shows sort of 2 semicircles overlapping, and in fact this turns to the right somewhat like in an exaggerated fashion, turns to the right somewhat like an inductive loop. Normally one would not apply 300 millivolts of perturbation amplitude, right, but here we want to exaggerate and see the features very clearly, see the difference between transformed and original data very clearly. Therefore, we have used very large perturbation amplitude. The code that is used to generate 1 millivolt can be used to generate 10 millivolts, 100 millivolts, any such amplitude. Okay. Since we are at 0.4 volt versus OCP, even when we apply 300 millivolt, the lowest point there, okay, if you assume this is 0, this is 0.4, 300 millivolt perturbation amplitude will still be 0.1 volt above the open circuit potential. Okay. So, this is still in the anodic regime. So, we do not have to worry about the cathodic reactions. This is the spectra that we get, and if we take 1 millivolt data and apply KKT, the simulated data is what we have shown earlier as blue color line, and the transform data we use the software provided by Professor McDonald and we get the KKT by integration, they pretty much overlap. So, you can say yes, this is not violating KKT, therefore, this is KKT compliant, and of course, we know it is coming from a small amplitude perturbation. So, we are fine. And if I take the data corresponding to 300 millivolt perturbation amplitude and plot the magnitude and phase as a function of frequency, it is Bode plot, I can see that the original data blue color line is different from the KK transform data. So, the transform data is dashed red color line, and you can see that for mid frequencies and at low frequencies you see a clear difference. Alright. So, we can claim that KKT can detect the nonlinear effect. See, once it is not compliant, KKT does not tell that the data is different from the original because of nonlinear effect or because of instability, it just says that it is not compliant. Okay. In this case, we know how the data was generated, therefore, we can say that nonlinear effect is detected. When you use the linear KKT software and compare the transform data and the original data, they overlap very well for 1 millivolt data, and at 300 millivolt there is a difference, especially at the mid frequencies. The magnitude appears to overlap very well, the phase is different, which basically tells you that there is a difference between the original data and the transform data. So, it is not KKT compliant. In case of linear KKT software, it is also good to look at the residuals. This also flags the nonlinear effect, but one can calculate the residuals. The residual in the real values are basically our simulation or original data minus the best fit measurement model approach best fit data divided by the modulus of the z, not z real or z imaginary, but actual z, which is z real plus j z imaginary. And likewise for the imaginary part, the numerator consists of imaginary part of the original data and the measurement model data or the linear KKT predicted data, and the denominator consists of mod of z. This is important because sometimes if you notice z imaginary may go through 0, may be close to 0. If you use z imaginary here, you will get a very large value here, and z imaginary, if it is exactly 0, it will in fact become infinity, and if there is a very slight variation between the transform data and the original data, we do not want that to appear as a large error. Okay. So, it is important to use mod of z rather than z real or z imaginary, and when you use this for 1 millivolt data, it is exactly 0. So, it means it is fitting perfectly. In case of the 300 millivolt data, the real and imaginary residuals are plotted as a function of frequency, and you can say this is probably 0 to 20, 0 to 10, maybe 10-15 percentage residuals. So, it is fairly large, and that is what appeared as a difference in the phase value here, and you can say yes, there is a significant difference. So, even if you take data in real experiments with some noise, you should still be able to see a significant clear deviation, systematic deviation between the linear KKT predicted data and the original data. All right. Now, we have taken the same mechanism and tried different sets of kinetic parameters, different sets of DC potentials, and in all cases you would get spectra. We have tested many, but we are showing a few here. Okay. This is second example, same mechanism, different set of kinetic parameters. Now, in this case we have taken the DC potential to be 0.5 volts versus OCP. We have tried 1 millivolt linear regime and 300 millivolt the non-linear regime. So, 1 millivolt data shows a high and mid frequency capacitor loop and a low frequency inductive loop. The large amplitude perturbation also gives you similar pattern, except that in the same scale it is not so visible, not so clear, but if you zoom in here you would see an inductive loop. It looks like it has shrunk. If I take the data at 1 millivolt and perform KKT by integration, the transform data and the original data will match very well. I am not showing it here, but when the system is linear, causal and stable, KKT by integration will give you a good match, especially when the frequency range is very wide. Because this is simulation, we can choose the frequency range to be very wide. We have chosen from 10 power 5 to 10 power minus 3, that is 100 kilohertz to 1 millihertz, and the data that we generate is KKT compliant. In this case, even when the data is generated with 300 millivolt perturbation, we find that it is KKT compliant. So, the real and imaginary part are phase and the magnitude. When I plot them in Bode plot for the original data and compare with the transform data, they overlay very well. KKT does not flag non-linearity in this case. Although by looking at this figure, you can clearly say yes, 1 millivolt data is different from the 300 millivolt data. So, why is it that in the previous case same mechanism, different sets of parameters, KKT is able to flag the non-linearity, and in this case it does not seem to flag the non-linearity. If I look at the linear KKT results, the same data 300 millivolt data, if I subject to linear KKT, there is a systematic residual. Okay. It is much smaller here though, it is plus or minus 1%. Previously it is 0% for 1 millivolt data and nearly 10-15% for 300 millivolt data. Here 1 millivolt data will give you 0% error, I am not showing it here, but 300 millivolt data shows maybe half percentage or at the most 1% variation. And if you have noise in the data, it is possible that the noise will subsume this, you may not see a clear systematic pattern. In any case, at least this is flagging it, but sensitivity is not as high as it was in the previous case. Next example is for a 3-step reaction, 2 adsorbed intermediates. So, the mechanism we have seen this, kinetic parameters we write it as 10 power minus 10, 15 for the first reaction, 3.3 10 power minus 12 and 20, 7 10 power minus 7, and of course third reaction is a chemical reaction. So, there is no B corresponding to that, and gamma is 10 power minus 7 moles per centimeter square. In this case, when we use 1 millivolt data, we get 2 semicircles. In case of 2 adsorbed intermediate, you may be able to get 3 semicircles, 3 capacitive loops, but for this set of parameters, visually if you observe, you can see 2 semicircles. When you go to large amplitude perturbation, this actually looks like a semicircle and this is like a distorted loop. I will not even call it a semicircle. And when we try KKT by integration, it shows a clear deviation, very large deviation in fact for the phase, and fairly large deviation for the magnitude. You have to remember the magnitude is plotted as log of the mod z. So, it goes from 10 power 0, 10 power 1, 2, 3 and 4, and of course, phase is in degrees. Okay. So, clearly this shows yes, this data is not KKT compliant. 1 millivolt data is KKT compliant, you have to believe me in that. And linear KKT definitely detects, whenever the KKT by integration detects, linear KKT detects. Even when KKT by integration does not detect the non-linearity, linear KKT detects the non-linearity, it is just that sensitivity is less. Now, the third part is the catalytic reaction. So, set of kinetic parameters here, B1 first reaction, forward reaction is with 0 volts, that means it is like a chemical reaction, although it is an electrochemical reaction, we say the transfer coefficient is 0. Reverse is minus 8, it is going to decrease, the reverse reaction will decrease with an increase in potential, therefore, it has a negative sign. B2 is plus 2, B minus 2 is minus 2, B3 of course is a chemical reaction, and B4 even though it is an electrochemical reaction, we are setting the B4 to 0. This is one set of kinetic parameters. Of course, you can try for a wide variety of kinetic parameters. And this is one of the examples where we see negative differential impedance. Comes like this. This is the high frequency, mid frequency and low frequency data. So, actually this is the origin. It is not very clear, so that zoomed in here. High frequency to mid frequency and then low frequency comes here. 1 millivolt data shows charge transfer resistance here and polarization resistance, which is probably in the range of 50, 100, 150, something in that range, and the charge transfer resistance is the range of about 20-25. When we go to large amplitude perturbation, the charge transfer resistance in this example decreases, but the polarization resistance, the magnitude increases. It is close to 400 ohms, the negative sign, ohm centimeter square. So, the actual value is lower, but the magnitude is larger. This case, since it goes to the left side on the complex plane plot, it goes to negative real values. We have to use the data in the admittance form and perform KKT by taking the data in the admittance form. Okay. So, we have to do KKT by integration using the admittance form. If you give it in the impedance form, even if it is KKT compliant, it is going to look like a mirror image. That transform data will look like the mirror image of the original data. Okay. So, what we have done is the following: we have got data in frequency Z real, Z imaginary, and of course, Z is given by Z real plus J Z imaginary, and Y is going to be inverse of Z. But instead of directly taking the simulated data, we have done the following. So, we have data at 100 kilohertz and of course, many intermediate values. This is going to be a very small number, close to 0, because we assume the solution resistance is not there, right. So, this is going to be a very small value, this is going to be a very small value, and when we take the inverse to find the admittance, it is going to be extremely large and numerical round of error will come in, and that means the admittance value, it is going to be a very large number. That is not easy to get accurate value in the MATLAB program or any programming environment. So, beyond a limit, when you use double or integer, whichever mode you use, it is going to be usually used in double, but it has a certain limitation on the accuracy. So, to avoid this problem, what we have done is to take that impedance data and generate new impedance data by saying Z real is Z real of this plus 100 ohms. Now, if I take this and substitute here and find the inverse, that is going to be a finite number, it is not going to be extremely large. So, essentially I take the data, and add 100 ohms to that, and then take the admittance form and process it. So, I can avoid some of this round of errors, and after doing that, notice the following: this is 10 power minus 3 and this is 10 power minus 2. So, if I take the inverse, it is going to be somewhere between 100 to 1000 ohms. Here, because this is admittance form, it is going to be in the range of 10 power minus 3 to 10 power minus 2. 1 millivolt data would come as KKT compliant. 300 millivolt data shows a clear difference here in the phase as well as the magnitude. Oftentimes, what people would do is take the impedance, invert it to get the admittance, perform KKT in the admittance form, get the transform admittance, and then invert it to get the impedance form and plot it. That is also fine. You can plot it in the impedance form, say that this is the simulated data and this is the transform data. In any case, you get a clear difference. So, in this case, KKT can flag the nonlinearity, and linear KKT also flags the nonlinearity. You have to remember to go to the software and choose the option to say that this has to be transformed in the admittance form, and then it will detect the nonlinearity clearly. 1 millivolt data will be KKT compliant when we transform in the admittance form. 300 millivolt data will not be KKT compliant, and of course, you always have to transform in the admittance form whenever the data goes to the negative side in the complex plane plot or left side in the complex plane plot. Now, after looking at this result, we know that sometimes KKT can detect, sometimes KKT cannot detect the nonlinearity. We looked at various possibilities, and this is the conclusions we have come to. First set of spectra, right, 1 millivolt and 300 millivolt, this KKT was able to detect the nonlinearity. If we plot the potential dynamic polarization plot, log current versus potential, current is in the log scale, and if I take 0.4 volt and if I use 300 millivolt range, this range log IDC versus EDC is not linear. Now, here is the thought process. If you take I versus E for a simple electron transfer reaction meaning reversible reaction, this is going to be exponential and this is going to be exponential. If I draw it as log, of course, I can't find the log of 0. If I go to a large enough potential and draw it as log I versus potential, this is linear, and I can even neglect the reverse reaction. And we know when log I versus E was linear, this reaction, the resulting spectra were KKT compliant for a simple electron transfer reaction. So, perhaps even in other reactions, if log I versus EDC is linear, maybe the spectra that we get would be KKT compliant, and if it is non-linear, perhaps it is not KKT compliant. So, with that hypothesis, we have checked. This case log I versus E with DC log I versus EDC, it is not linear, and this is not KKT compliant. If you look at the second set of data, if I look at log I versus EDC, it is linear, and KKT by integration is not able to detect this violation of linearity, and linear KKT can detect it, but it is less sensitive. 3-step reaction with 2 adsorbed intermediate. Again, at 0.5 volts, if I go to 300 millivolt range, it is not linear. Log I versus EDC is not linear. Here at 0.6 volts, of course, it has a negative slope. That is why the low frequency impedance settles at negative real values. And this also, if I go to plus or minus 300 millivolts, 0.6 plus or minus 300 is actually fairly large, it is non-linear. So, the hypothesis is that whenever log I versus E is non-linear, KKT by integration can detect the non-linearities. Linear KKT software can detect the violation of linearity if ln I or natural log I versus EDC is linear, then KKT by integration does not seem to detect it, and even linear KKT detects it, but with less sensitivity. Okay. We had tried it for few more kinetic parameter values, few more sets of kinetic parameter values, and in all cases it seems to work. So, based on this empirical study, we think this is true. Next, okay, we know how to generate the spectrum incorporating the instability effects or drifts. We have seen this in the previous class. So, I want to show you an example where we have taken the simple electron transfer reaction and we apply a exponential drift. Okay. This is published in 2011 by our group, and we have seen before that if you have 10 millivolts or 100 millivolts drift, maximum possible drift with a particular B value, this is the data that you would get, and if it is minus 100 millivolts, it is going to look like a, in a proper scale it is going to look like this, in a distorted scale it is going to look like this. If I take this data and apply KK transform, I will always find that KKT will show that the data is not KKT compliant. here the lines are the original or simulated data and the symbols here are the transform data. These are the transform data. Okay. Here I have plotted z real versus frequency and z imaginary versus frequency. It is not that common, but it is also done sometimes. The main point is the original data and the transform data do not match, especially at the low frequencies. Okay. You can also see in the high frequency region, the stable, which is shown by a continuous line, and the points which correspond to the unstable system, they are more or less the same. So, at the high and mid frequencies there is not much of a difference between the stable and unstable system. At the low frequencies you see a clear change, and that is shown in the transform data also. At the low frequencies it deviates. Okay. And whatever cases we have tried, whenever there is instability, KKT is able to flag this, whether we use KKT by integration or KKT by linear KKT software. Okay. Next, normally when we say that system is stable, what we mean is the following. We have a DC potential, we apply an AC potential. If we stop the perturbation and wait for some time, the system should come back to the original condition, then we would call that as a stable system. Okay. Now, there is a subtle thing. When we apply AC potential, we have seen that it does not give you steady periodic results immediately. It can take some time for us to get the steady periodic results. Now, I apply AC potential on top of DC. Okay. The current would do this and then settle, or do this and settle. Now, if I stop applying the AC potential here and wait, it would come to the original condition, the system would revert back to the original condition. However, if you record the data here and call that as impedance, then normally one would not say that the system is unstable, system is stable, because when I apply a perturbation it responds, when I stop the perturbation it goes back to the original condition, that is all right. But there is one more point, that is when you record the data, that should come from steady periodic result. If you take the data before the system achieves steady periodic condition, then what happens is this. We have looked at the data like this. If you get results after steady periodic conditions, the green color line is what you would record. If you take the data before coming to steady periodic condition, if you take the data in the first few loops, maybe first loop or first few loops, at high frequencies and at low frequencies you will not see much of a difference for different reasons. At high frequency, because majority of the current goes through the double layer capacitance. At low frequencies, because system would come to stable condition even before half loop is completed. At mid frequencies, a significant current goes through the Faraday process and system would not have come to stable condition or steady periodic result. So, there is a difference. If I take the data that is under what I call as drifting condition, you can also say before coming to steady periodic results, initial conditions, and perform the KKT by integration, what we see is the following. Z real, there is a significant difference. Imaginary, there is slight difference, it is not very clear in this scale, but KKT will show a difference even though this is 10 millivolt data. And if you take the stable data, it will be KKT compliant. If you take the data in the initial condition where it is not giving you steady periodic result, this data will not be KKT compliant. So, if you look at this, if you just look at the overall definition of is the system stable or unstable, normally people would say that this is stable, but the data should also be acquired under steady periodic response. If it is acquired during the initial condition where it is not reached steady periodic results, that data will not be KKT compliant. Okay. So, in summary, based on empirical evidence, that means we have not shown theoretically that when log I versus E is a straight line, when it is linear, the violations of linearity will not be captured by KKT. KKT will not flag the spectrum acquired at large amplitude perturbations. But with a number of simulations, what we conclude is that if log I versus EDC is nonlinear near the EDC where the spectrum is acquired, then KKT by integration will flag the nonlinearities. Okay. Linear KKT software always flag the nonlinearities. However, if this comes from a system where log I versus EDC is linear, then the sensitivity is less. And when you look at the instability, when a system is unstable, KKT will always flag it, whether it is linear KKT or by integration. And even when the system returns to the original conditions, if we acquire data during the time where the system has not settled and has not begun to give steady periodic response, then also KKT will flag the spectrum. So, KKT is actually very sensitive to stability criteria. Okay. We will stop here today.